Hello everyone. Welcome back. So this is our third lecture for the partial differential equations. Today we're gonna discuss about the derivations of the heat equations in a 2D and a 3D dimensions. So recall what we have done in this first two lectures. First, we derived the heat equations using the concepts that we know from physics and chemistry, basic concepts, and we try to construct our partial differential equations. And then, since we're dealing with some two unknown functions, we need to only have one. Again, we go further through using some properties of the heat flow and some new laws, and we're able to construct our differential equations with just only one unknown functions. Therefore, we have also talked about the boundary conditions, the importance of the boundary conditions, how the boundary conditions can help us to solve our differential equations, and also using the different types of the boundary conditions and then the different boundary conditions, how the different solutions. And we did one example specifically for the equilibrium, in the steady state conditions. How does this help us to determine our temperature, the equation of the solution in our PDEs. But so far, what we have done mostly, it was just that we had the independent variables of x and time, position and time. Now we're gonna so we talked only about the one dimension. Now we're gonna talk about the three dimensional, where instead of only one position, we're looking for two other coordinates, x, y, and z. So now let's consider arbitrary subregion R. So suppose that R has the shape like this. Okay, we can draw it like something like this. So suppose we just have a arbitrary region R. Okay, so this is our R. Like in 1D conservation of heat equation, in a 3D, again, conceptually, our rate of change of heat energy is equal to the heat energy flowing across the boundaries per unit of time plus the heat energy generated inside per unit of time. Okay, so now let's again, how we decompose each parts and then try to figure out the expression for that. And now we're gonna do the same thing in this in a 3 dimension. So the heat energy within the arbitrary subregion R. So it's gonna be how we started the heat energy. We just did, if you remember, the energy density multiplied with a volume. multiplied with the volume. And our volume was the cross-section area multiplied to its length. But now, in this case, our volume is just going to be the volume integral. So we're going to define that our energy density, so the volume integral within that subregion and dV. Now what will be our energy density? If you remember from the previous lectures, our energy density was just the heat capacity times the mass density times the temperature. Was the previous lectures for the derivations. So far we have the rate of change of heat energy. So we have the heat energy within the subregion, and therefore for the rate of change of heat energy, you just have to take the the derivatives with respect of this with respect to time. Now, for the other concepts, we have to introduce and recall some of the theorems that you might learn in a vector calculus. Okay, so let's talk about heat flux vector, and normal vector. Normal vectors. So our heat flux vector is gonna be symbolized as our heat flux, well, the vector symbol. The magnitude represents the amount of heat energy flowing per unit of time per unit of surface area. Now, considering the conservation of heat energy, considering the heat energy, our heat flux is just the heat flowing across the boundaries per unit of time. The heat flux is the heat flowing across boundaries per unit of time. Okay, now, so let me just draw the same diagram here. Now, suppose we choose to write this point. So suppose we have the heat flux pointing this direction. Okay, so this is our heat flux. Now, let's say at this point right here, this is our heat flux. And let's consider this point right here, which is just perpendicular to the surface. Now, let's consider these 2 points right here. This point I'll call A, and this point I'll call B. Okay. In point A, at point A, the heat flux is just parallel. The heat flow is just parallel to the boundary, or the tangent to the boundary. So therefore, there's no heat energy is crossing the boundaries at that point. At that point, there's no heat energy is crossing at that boundaries. And that makes sense, kind of, right? Because it's just going over the wall and that's it. Nothing happened. No heat energy there. while at point B, our heat energy is just a perpendicular to our surface. So the only normal component of our heat flow that contributes all of this arrows is contributes, the heat flow is contributes into this point right here. But now for the heat energy, we only care about the normal vector, the normal component that also contributes. Like suppose if I choose this point right here, this is the, okay, now this is my heat energy, right? That's my heat flux. Now if I draw the perpendicular line, at this point, this blue line is my heat flow. This is my angle theta. Now I only care about the normal vector. So that's gonna be, let me show it in black, it's gonna be my heat flow in the direction of the normal vector. We only care about the normal component of the heat, or normal component, because that's the only normal component that contributes. Only normal component that it contributes. So I will note here only normal component of heat flow contributes. So now you're gonna ask a question, but at any point we have two normal vectors. One normal vector is going inward. Let me choose this point right here. Right? One normal vector is going inward. One normal vector is going out. So this is out, and this is only in. Every point has these two normal vectors. The only vector that you have to worry about is the outward normal vector. So here also note that use only outward normal vector. Only use the outward normal vector, because that also makes sense. Now, let's go. So this is all we need to know about the geometry within this region that we're going to use it to derive our heat equation. Now, at each point, so now let's go back to our conservation point. If you notice at this point, the amount of heat energy flowing out of that region per unit of time is, per unit surface area, is our outward normal component of the heat flux vector. Now, at this point, let me call it C. I don't know why I didn't call it. Now, at this point, at point C, the outward normal vector, it just has the cosine component. Is the magnitude of the phi and the normal vector. There's something wrong in this picture. It should be this should be our theta. Because if that's my phi, this is my normal vector, this should be my theta. So my phi of cosine is just equal to my phi times the normal vector over its magnitude. So this is the unit vector. So multiply the unit vector, unit normal vector. If our dot product is negative, so it's going the opposite direction, so that means our flux is invert. But now this is not what we care about. Now the only thing we have to care about, since our heat flux is just defined as the amount of heat energy flowing out per unit time per unit surface area. So let me just write that. Our phi defined as the amount of heat energy flowing out per unit time per unit surface area now per unit of time per unit surface area. So now in order to determine the amount of heat energy, to determine this component, so we want the in a rate of time, change in time. But since our phi has an extra surface area, we just have to find the amount of heat energies, the component, the vector component that contributes to heat energy, multiply to its surface area. Now we're talking about in a closed surface, in this enclosed region. So therefore, I can say that my the total heat energy per unit of time, which is the heat energy flowing across which is in this case this total doesn't refer to the total amount of energies that here. It refers the total energy flowing across the boundaries. So more correctly, it will be easier if I just write this. So across the boundaries, it's just gonna be my surface area integral, the normal component of my heat vector multiplied ds. So that's the second part that I have to worry about. Now let's go about the third part. Now, let me just zoom in here. Now, since if you remember, the Q is the amount of which is the rate of heat energy generated per unit of volume. Therefore, I can say that my third part, which is the total heat energy that generated, the heat energy generated in the region per unit time is just equal to my Q multiply to the volume component. So therefore, now whatever I have everything here, I'm gonna rewrite that into my heat equation. Now I substitute all the symbols I have into instead of my words. So conservation of heat energy become time derivative of my volume integral C rho U dV. That's equal to now the amount of heat energy that's flowing out, so it's going to be negative. So ds, and the plus, the one that I care about is the generated R Q dV. Now this part and this part seems fine, right? If I combine them, now I have to worry about this part. How can I rearrange this? Very simple. Now in vector calculus, you remember this theorem called the divergence theorem. So recall the divergence theorem, which is also known as the Gauss theorem as well. The divergence theorem states that the volume integral of the divergence of any continuously differentiable vector A is equal to the closed surface integral of the outward normal component of that corresponding vector. Okay, just rewrite this part right here. It's just the corresponding the outward normal vector of that corresponding vector. So therefore, I can rewrite my conservation of heat now because therefore my conservation of heat energy becomes d dt of 0 u dv, that's equal to negative. Now my volume integral of the divergence of my heat flux and plus the volume integral of my heat energy that's generated. Now I can take everything to the one side. So assume that the heat capacity and the density are time independent. Not assume, they are time independent. So therefore my R, so I have 0 partial u partial t plus the gradient, the divergence of my vector dv minus q dv is equal to 0. And from here, therefore my conservation of heat Therefore, I can write that my 0 partial u partial t is just equal to negative partial phi plus q. Okay. Again, now we still have two unknown functions, and if you remember conservation of heat, we only need the u in terms of u. So apply the similarly Fourier's law of heat conduction. Now, since in a Fourier's law that we have here was in a one dimension, now we only care about the two dimension or three dimensions. So in this case, our heat law is just the gradient of my given function. Now, why is gradient and not the divergent? Okay, you might ask. So critically think about this. My phi is a vector, right? My phi is a vector. My temperature is a scalar. So I cannot take the divergence of the scalar. To make my scalar into a vector, I just have to do a gradient of my scalar function in order to get my corresponding vector. So therefore, apply the Fourier's law of heat conduction. Therefore, the phi is equal to negative of the gradient of my scalar u. Now I can substitute this into my equation. Therefore, I have 0 partial u partial t that's equal to the negative dot negative k0 so u plus q, and therefore my heat equation is just become 0 partial u partial t is equal to k0 my Laplacian of my u plus q. Okay, here we go. Now this is my heat equation in the 3D. So now let's again talk about the boundary conditions. So I will talk about the initial boundary volume problem. So let's say our initial condition. Now my initial condition will be look like as u, x, y, z at t equal to 0. Now I can define as a function of f that's x, y, and z. I will just put a small note here that this is t, so no confusion in the further derivations. So now my now this is my initial condition. Now for boundary condition, I will use my prescribed temperature, and I can say, okay, let's say my prescribed temperature yz at time t is just defined as a temperature x, y, z, and t. All of this now. Now it is like possible that the flow across the boundary is prescribed. So the most common one, if the boundary is insulated, so there's no heat flow again. So now our gradient is equal to 0. Now, like we did in it. So now for insulation, for if the boundary is insulated, therefore my partial u with the normal component of that is equal to 0. Okay, so far everything is just the same thing, but now we are looking for in a 3D version. And then similarly, the Newton's laws of cooling, which contains both the unknown function and the derivative of the unknown function. Now, since the Newton's laws of cooling states that the heat energy flowed out per unit of time per unit of surface area is proportional to the difference between the temperature of the surface and the temperature of the outside of the surface. And everything that we learned, so it's a k naught, the gradient my u, the normal component is equal to the coefficient of convection, the temperature of the surface minus the temperature of the outside. Okay. Everything is the same thing again, but just the symbols that slightly changes. And we talk about the vectors. Steady state. The steady state condition. If the boundary condition and any sources of thermal energy are independent of the time, it's possible that there exists a steady state solution to our heat equation. Now, we know that steady state condition is the time independent again. So I can say that my partial u, partial t is equal to 0. Therefore, my k naught Laplacian of u plus q is equal to 0. And therefore, if I solve it, I get my Laplacian of u is equal to negative q over k naught. Also recall that this is the same as this. This is also called a Laplacian. But sometimes be careful, because sometimes they use as a changing, like final minus initial. But sometimes in the books, in the vector calculus, they wrote this in terms of this. So I just wrote this so you prevent from the confusions from the changing with the Laplacian. This equation, as I showed it, let me just write this for a moment here. This equation is the Poisson's equation. Poisson's equation. I used to call this Poisson's equation. Well, childish behavior, I know. Now, if there was no sources, therefore, my Laplacian of my temperature is equal to 0. And this is called the Laplace equation. Laplace equation. The interesting thing, this is very similar to in electromagnetism when you study about the electric potential. Again, it's the same thing, same meaning, same differential equation. It's just in a different categories. So your math background must be good. So if you understand PDEs, you can solve very easily about the electromagnetisms, and quantum mechanics is basically ODEs. Sometimes they are PDEs too. But this Laplace equation and Poisson equation, that future if I talk about electromagnetism, you're gonna make it again, but for in terms of electric potential, not the temperature. So basically, Poisson's Laplace didn't study the temperature itself, they study all of these PDEs, and it's applicable for everywhere you use it. And also do not forget about that if you're using a cylindrical or spherical, when you do the integration, the volume integration, it is sometimes convenient and makes it easier to use the cylindrical and spherical coordinates. And to derive that formula, in the future, I will. That's one of my plans. Using the curvilinear space to derive the Laplacian, the divergence, and the curl in the spherical and cylindrical coordinates. But for right now, just we have to worry about the partial differential equations. Okay. So for today's lectures, this is our today's lectures. We're going to end here, and we are done on the basic concepts of the PDEs. And the future, then the next lecture of the PDEs, we're gonna use our first method, which is called the method of separations of variables, which you might learn you might remember in ODEs. We're gonna use the same basic principles, but there are some kind of stuff that it requires to consider in order to apply for that. Thank you so much. I upload the lecture notes in the Instagram, which is right below. Thank you so much. Have a great night.